Hello and welcome to a wrap-up lecture about the Fourier transforms, where I want to discuss a few things that I didn't talk about earlier, but I think they are important enough for us to just touch on those subjects. So I define the Fourier transform as an operation from the space L2 to the space L2. There's several exceptions to this rule, one of which is the delta function and another as the exponential functions sine and cosine. They are not L2 functions, but we can define Fourier transforms for them in the sense of distributions. What is a Fourier transform of a delta function? A delta function is, as I said, is a model of a impact action on a physical system. So if I compute the integral Fourier transform of a delta function, it is by definition the integral from minus infinity to infinity of the delta function of t minus alpha times e to the minus I omega t dt. And by the property of the delta function, this is simply e to the minus I alpha omega. In particular, the Fourier transform of just the delta function when alpha is 0 becomes 1. Neither the delta function nor a function 1 are members of L2, but this example of Fourier transform has a physical meaning. It looks like the delta function has all of the frequencies present in it, and all of the frequencies have the same magnitude. One of the implications is the inverse Fourier transform of 1 must be delta function. What I mean by that is 1 over 2 pi, the integral from minus infinity to infinity of 1 times e to the positive I omega t d omega must be the delta function of t. I'm going to play a little trick here. I'm going to replace the omegas with t's and t's with omegas. So omega is going to be replaced with minus t, and t is going to be replaced with omega. So this means that 1 over 2 pi, the integral, if I replace omega with minus t, then that means that when omega is minus infinity, the lower limit of integration becomes positive infinity to minus infinity. I get 1 times e to the I times minus t. T is replaced with omega and d minus t. And this must be t is replaced with omega, so it's just delta function of omega. Changing things around, I get that the integral from minus infinity to infinity of 1 times e to the minus I omega t dt will be 2 pi delta of omega. So it seems like the Fourier transform of 1 is a delta function. Again, neither 1 nor delta function members of L2, so these Fourier transforms are defined in the sense of distribution. So if I have a signal that's always 1, then it has only one frequency present in it. It's the frequency 0, and it has infinite amplitude of that 0 frequency because the energy of the signal 1 is spread over an infinite interval. What I arrive to is that the Fourier transform of 1 is 2 pi delta of omega. And we also learned a neat little trick that it seems like the Fourier transform and the inverse Fourier transform, since they're the same kind of integration, they're kind of interchangeable and they have a symmetry to it. So if the function a generates a Fourier transform of a type b, then if I take a type b function in the time domain, then it would probably generate a Fourier transform of type a in the frequency domain. Okay, I can build on this example and compute the Fourier transform of the function e to the I alpha and sines and cosines. So for the Fourier transform of the function f of e to the I alpha t, I'm going to use a shift function and say that this is the Fourier transform of 1 and then omega is shifted by alpha, and the Fourier transform of 1 is delta function, so it's going to be 2 pi delta function of omega minus alpha. And this is quite expected. I have an infinite time signal e to the I alpha t that oscillates, has magnitude 1, has amplitude 1. I mean, oscillates as a complex valued function, so it has only one frequency present in it. It's the frequency alpha, and it has infinite energy of this frequency because it goes on forever. Now I can use the e to the I alpha t to generate the Fourier transform of sine and cosine. So I can write that sine of alpha t is the same as e to the positive alpha t minus e to the minus alpha t divided by 2i. Therefore, the Fourier transform of sine of alpha t is just a summation, a linear combination of two delta functions. So it's 1 over 2i multiplied by 2 pi, so it's going to be pi over I, and then I have a delta function of omega minus alpha for the e to the alpha t minus a delta function with omega plus alpha for e to the minus alpha t term. And the Fourier transform of cosine can be computed in a similar fashion. So it's going to be 2 pi over 2, so it's just pi times a delta function of omega minus alpha plus a delta function of omega plus alpha. We can view it in this way. The Fourier transform tells us which frequencies are present in the signal, and both sine of alpha t and the cosine of alpha t have only one frequency present in it, the frequency alpha. But since the frequencies alpha and the negative alpha for both sine and cosine kind of mean the same signal, then also the frequencies negative alpha are present in both the Fourier transform of sine and cosine. And both of those frequencies get the infinite energy because both sine and cosine are infinitely long signals when t goes from minus infinity to infinity. So one thing I would suggest you to experiment to help you with one of the problems on the test guide is to try to compute the Fourier transform of a function h of t plus 1 minus h of t minus 1. So this is going to be the Fourier transform of a step function that steps up and down at the points minus 1 and 1. I did compute this Fourier transform on one of the examples, but now what you have to do is to use the trick I introduced in example 1 when you reverse the places of the forward Fourier transform of the inverse Fourier transform to get the Fourier transforms of other functions. So this is going to help you with finding the inverse Fourier transform of a function sine t over t. And the last thing that I didn't talk about, but I want to kind of mention it, is about the discrete Fourier transform, and it's the fact that the discrete Fourier transform can be expressed as a matrix operation. Remember, I defined the discrete Fourier transform of a signal as a summation as j goes from 0 to capital N minus 1, and I'm going through the samples of the function times e to the minus I 2 pi k over n j. I also said that this can be expressed as a dot product of f with the vectors wk. But let's look at it from a different perspective. We can see it as a vector fj being multiplied by a bunch of numbers. So I can view the vector f as a column vector, and then take all of those numbers, e to the minus I 2 pi k j over n, and write them as a bunch of rows. This can be viewed as when k is 0, it's going to be multiplication of f naught with e to the minus I times 2 pi times 0 over n times 0. Then the next component is e to the minus I 2 pi times k, so it's still 0, but j is now 1. And then the last component in this row is going to be e to the minus I 2 pi, k is still 0 over n times j being n minus 1. Well, the next row will have k equals 1, so we'll have e to the minus I 2 pi times 1 over n times 0, e to the minus I, then I have 2 pi times 1 over n times 1 for j being 1, all the way to e to the minus I 2 pi 1 over n times n minus 1. And I keep populating the rows, and as you can see, this is exactly the matrix multiplication. So we can say that the Fourier transform vector is going to be a multiplication between the vector f and the capital F, where matrix F has its components with the rows indexed by k and the columns indexed by j to be the exponential terms e to the minus I 2 pi k times j over capital N. You can see that the matrix is symmetric, is equal f jk, therefore f is symmetric. We also know that every single row is orthogonal to every other row, so if you multiply a row by another row with a complex conjugation, the inner product can be written as wk multiplied by wj bar transposed in a matrix multiplication operation, and we know that all of those are 0 if k is not the same as j. Then it seems like if I take f and multiply it by f transpose, so all of the rows become now columns, and then I also complete the complex conjugate, then I will get the matrix with zeros everywhere but the main diagonal. And on the main diagonal I will have dot products of wk with wk, and we already computed that all of those inner products of the vectors wk with themselves are just n, so it's n times the identity of size n by n. So therefore f inverse is 1 over capital N f bar transposed, and therefore the inverse Fourier transform is simply 1 over n times f bar transposed times the vector of the Fourier transforms. The convolution operation can be similarly expressed as a matrix operation, but expressing everything as a matrix operation is a very inefficient way to actually compute it. So this doesn't make much sense from the computational point of view, and also it's not that useful from the theoretical point of view. So I'm going to skip the matrix definition of the convolution since it's not very useful. But in terms of the Fourier transform, viewing the discrete Fourier transform as a matrix operation can actually introduce a convenient framework to verify certain computations and check properties of the computations that you're doing. So this officially is the end of the Fourier transform series of these lectures. Thank you for listening, and I'll see you in our next video.